Okay, good morning. Uh, Welcome to this last lecture of the ML part. And in this lecture, we are planning to cover linear discriminant analysis. And with this, I think this course series will have almost all lectures beautifully presented for each of the topics, which will help you for the exam. It's a short topic actually, LDA. It's not so. I thought there's not much detail we have to go into LDA, but turns out it's actually less what you have in your syllabus. So I'll explain you the concept, and today I'm kind of trying to plan a 20 question marathon. Okay, 20 questions marathon about let's see 1 hour, 1 hour, 30 minutes, how long it takes. But that will help you to gain some important tricks, some techniques you will learn how to solve the problems given in the exam. They are questions taken from the internet, from my own source, like from me, or they are the previous year gate questions. So this is what it is. So let's begin with the topic of discussion for today, which is LDA. Okay. Okay. So yesterday we looked at principal component analysis, PCA, and the main thing about PCA is to reduce the dimensionality of the data by maximizing the variance of the transform dimension. By maximizing the variance of the transform dimension. Now, when it comes to linear discriminant analysis, we are in the territory of supervised learning. And when you are in the territory of supervised learning, we have typically one of the examples is a data set with two known categories. Okay, we have a data set with two known categories or two known classes. It's a binary classification problem. And that means now what we want to do is we want to maximize the separability between categories. We want to maximize the separability between categories. Also, it's a dimensionality reduction problem. Okay. Now, one of the basic questions is if PCA was working absolutely okay, what is we want to actually try to achieve by doing maximizing the separability between the different categories? See, let's take an example data set. Okay. Okay. And let's say there are two classes. Red denotes one class. Okay. So I'll plot the points of the red class. Okay. And I'll point, there's another class, I'll call it green class. The points are like this. Okay. Now, by just looking at this, can you say whether these two lines are linearly separable? Which is, can you draw a line that separates out these two classes? And we can clearly see that. So let's say this is the dimension x1, this is the dimension x2, right? This is a line that I can draw here. Let's say this is one of the lines, right? that linearly separates these two classes. Okay, that linearly separates these two classes. Now my idea would be that when I'm trying to reduce the dimensions, let's say I'm trying to reduce this to a one-dimensional data set, one-dimensional, what shall I say, one-dimensional number line. My classes, the separation that is present in this case, if the separation is also there in the reduced dimension, then it's a very good thing, right? Even I'm able to reduce the dimension as well as make the class linearly separable. Now you might think that, boss, PCA, then why doesn't it do? Because PCA does not try to maximize the separability between classes. PCA only maximizes the variance. Let's say the PCA tries to project the points in this line. Let's say, okay, the same line as the line I drew for the separation of classes. Let's say PCA wants to project these points on the line. So what it will do is it will project this point here, 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 here. Okay. And what would PCA do then? PCA will draw you a single line. Okay. And what happens here is, see. So this point is here. So I maybe there that is this point here. Then this point here, right? Then we have a green point here. 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 And for the red points, it will be like this. One will be here, as you can see, right? One will be here, 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 one will be here. So when I try to reduce the dimension using PCA, the reduced data set is no longer linearly separable. So if I want to fit a line that separates these two classes, I cannot do so for the reduced data set. Okay. Okay. So can I try to reduce? So the goal is to find a projection on a line that find the projection on a line such that the samples of different categories remain linearly separable. Okay. When I find a projection on a line in such a manner that the samples present from different categories or classes, they remain linearly separable. Okay, this is the goal of LDA, linear discriminant analysis. Okay, okay. Now let's draw the same data set again here. Now the idea is how to do this, right? So let's draw the same data set here. Okay. We have the two classes, red and green. So this is the red class. Okay. And this is the green class. Okay. Now this red class has a mean, let's call it mu1. Okay, the mean of the data points, let's say it's mu1. And for the green class, it is mu2. So what I can do is I can project this on the XY axis, the mean. Okay, let's say this is mu1 tilde, and I can project this on the x-axis and I call it mu1 cap. Okay, similarly for mu2, I may have, let me change the color so that you understand. Okay, so, okay, which color? Let's say this. So I was saying mu2, okay. There is a projection of mu2 on the x-axis, I call it mu2 cap. And the projection of mu2 on the y-axis, I call it mu2 tilde. Okay. Now, just by looking at this, you might think that if we try to separate the two classes, we may want to maximize the separation between the means. Maximizing of separation of means. Right? Which also means I will maximize the difference between mu1 tilde minus mu2 tilde. Which means, I mean, even this you can call it tilde, so that I just want to maximize the separation between the two classes. If you look carefully, right, in this case, in this example that I have written here, I have two options. Either I can project the points along the, let's say this is the x-axis, this is the y-axis. So I can project the points along the x-axis, which is one option. So I might project the points along the x-axis. In case u1, okay, I think we have to introduce it back. In case u1 cap and u2 cap is maximum, more than u1 tilde minus u2 tilde. Otherwise, I will have to project on the y-axis line. Now, if I ask you the question among these two lines, which is upon projection along the x or projection along the y, which one is actually linearly separating the classes? I think it is fairly easy to say. If I project the points on the y-axis line, then I may be able to, then I'm able to linearly separate the classes. But if I project it on the x-axis line, then I am not able to separate. Right? So again, the same problem of PC that comes up. And also, the main thing that you have to see here is among these two means, it is clearly observed that the difference of u1 cap minus u2 cap is more. And this algorithm, if I just try to maximize the separation of means, will actually project the points along the x-axis. X-axis. Okay, so we are back to the same problem. And maybe you will think that I was joking all this time, but no. There is one important thing that you will have to consider here as well. Look at the spread of the data, the variance, the scatter. If you look at the spread, this here data is having a variance like this on the y-axis. On the x-axis, the variance is like this. Okay. Now, the smaller the variance, the better it will be linearly separable. So we also want to consider variance here to some extent. To some extent, meaning we want to still maximize the separation between the means of the two classes so that they are maximally far apart. But also, we want to make sure that we want to go through that points, we want to project the points on that line which have smaller variance. Okay, so maximization of separation of means does not consider the variance of the classes. It's obvious, right? Because you're only considering the mean. Okay, so we also want to bring in variance to this picture. Okay, any questions before I continue? No? Okay. So now let's set up the problem. I'll just pull this a bit up. Okay. Yeah, this looks okay. Yeah, just that. Okay. And I'm lazy to write y again, so I try to make sure the order is same. Okay. So suppose okay, this is the problem setup. Okay, there are two classes. So number of categories or number of classes, I call it classes. Okay, which is the number of classes is 2. So the class set is either a category can belong to class 1 or it can belong to class 2. Okay, number of classes are 2. There are n samples. Okay, with number of dimensions as small d. D-dimensional, there are n samples. Now, number of samples from class C1, second, number of samples from class C1 is N1. Okay, and the number of samples C2 is N2. N1 samples from class 1, N2 samples from class 2. Okay, now if xi is a data point, which is one of the samples xi. Okay. The projection that is of that point xi on the line, the projection on the line is given by the unit vector v. Okay, is given by the unit vector v, and this is high school math, v transpose xi. Okay, then the magnitude. And one more thing, let mu1 and mu2 denote the mean of samples of C1 and C2 before projection and mu1 bar and mu2 tilde denote the mean after projection. Okay, denote the mean after the projection. So I can say that u1 tilde is 1 by n1. There are n1 samples of class 1. Summation xi belongs to class 1 v transpose xi. This is a unit vector given in the direction of v. I can pull the v transpose out, 1 by n1 summation of xi belongs to class c1 xi. Okay, and now what is this term? The summation. This is nothing but the mean, right? The mu1 before projection. So I can write this as v transpose mu1. Okay. Okay, understood, right? Because this term here denotes the mean mu1 before the projection. Similarly, for mu2 will be 1 by n1 summation of, 1 by n2 because it's mu2 samples belonging to class 2 v transpose xi, and if you do the same thing, so v transpose 1 by n2 summation xi belongs to c2 xi is nothing but v transpose mu2. Okay, this is the sample mean after projection expressed in terms of the sample mean before the projection. Now in the LDA, we need to normalize we need to normalize the difference in mean, right? The difference in mean, which is absolute value of u1 minus u2, the difference in mean by the scatter. Now, what is a scatter? Okay, so what is a scatter? So before I introduce that, I'll just write one small thing here. Let yi equal to v transpose xi be the projected sample of xi. I just name the thing as yi. Okay. Okay. So the scatter for C1 is S1 square tilde is equal to summation yi belongs to C1. So all those projected samples of class C1, what is the difference of yi with the new mean mu1 bar, mu1 tilde squared? Okay, this is nothing but sort of variance, because if variance was there, I would have divided it, right? But no. So class C1 is this, and sorry, and for C2 is square equal to all the samples that belong to class C2 yi minus mu2 tilde whole square. Okay. Okay. This is the scatter. So the goal is to project the line on the data having direction given by the unit vector v that maximizes. So what is the cost function now? So the cost function j of v is, I try to maximize the difference in the mean. So u1 minus u2 tilde square divided by I want to normalize it with respect to the scatter. S1 square tilde plus S2 square tilde. Okay, I want to maximize this. And the idea is, if we try to find the v, the unit vector v that maximizes this up cost function jv, then we are guaranteed that the classes will always be linearly well separated. Okay. 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 Now, how much slides do I have? Oh, I have not. Okay, I will be able to write. Okay, or else I would have uploaded it while I was teaching so that its time is not wasted. Okay, so I think that's the whole problem. Now, before the projection, okay, before the projection, the scatter matrix S1 is summation xi belongs to C1. So this is straightforward statistics, right? Xi minus mu1, xi minus mu1 transpose. Okay. Similarly, for S2, we have summation xi belongs to C2. This is just trying to find the covariance, the sorry, the variance of the sample across the two different, so mu2 classes. Okay. Now we define something called, within class scatter matrix given by SW. Let me just define this. And the SW is nothing but S1 plus S2. Okay. So with this notation, I can say that my S1 tilde square, right, is nothing but V transpose S1 V, and S2 tilde squared is V transpose S2 V. So if I want to calculate the within class scatter matrix for the projected sample, S1 square plus S2 square, I can write this as V transpose S1 plus S2 V. And now what is S1 plus S2? S1 plus S2 is SW. So I can write this as V transpose SW V. Okay, let's say this is 1. Okay, now we do another definition. We define another term. Between class scatter matrix given by SB. Okay. Now SB is nothing but U1 minus U2, U1 minus U2 transpose. It's a dot product between the two mean vectors, the difference between the two mean vectors. Similarly, if I want to calculate U1 minus U2 squared, right, I just removed the absolute sign because it's the same, right? If you just do square, it will anyway take the positive always. So if I do this, u1 on the direction of v, projection will be v transpose u1. Sorry, I'm trying to do u1 tilde minus u2 tilde square. So u1 tilde, which is a projection of u1 along the unit vector v, will be v transpose u1 minus v transpose u2, projection of u2 on the line given by unit vector v. And so I can write this as v transpose u1 minus u2, u1 minus u2 transpose v. Okay, and now what is this? We already defined it. We defined it as the between class scatter matrix. So I can write this as v transpose s v v. Between class scatter matrix s v v, and let's say this is 2. Now I want to substitute 1 and 2 in JV. Okay, so what was JV? JV was u1 minus u2 beta squared divided by s1 squared tilde plus s2 squared tilde. Okay, now I can write this as v transpose SBV divided by v transpose SWV. So just to explain, this comes from 2, this comes from 1. Okay, okay. Now I want to, as I say, maximize this. So this is based on and find the v, or maybe I just write this down so that it's in your notes, right? So uh, the goal is to find the unit vector v, right, that maximizes j of v, okay, such that classes are linearly separable. Okay, such that classes are linearly separable. Okay, I'll just drink some water. You guys have any questions? Let me know. Yeah, so the we try to maximize JV, right? And classes are linearly separable. Okay, so again, it's a maxima minima problem, right? So we do differentiation, equate it to 0. So dJV divided by dV is equal to 0. So if we differentiate, it's a U by V rule, right? You might know this. So we get SBV minus V transpose SBV SWV divided by V transpose SWV, and I equate it to 0. And if you do some simplifications, you get SBV minus, now the thing is, this is a scalar. And I call this lambda. SWV is equal to 0. And then I can do is, I can equate it SBV is equal to lambda of SWV. And let's bring SW to this side. I can write this as SW inverse SBV is equal to lambda V. Okay, now does this sound something that you have seen before in linear algebra? Absolutely. So this is the eigenvalue, eigenvector. This is the matrix, I call it M, and this is the vector V. So we are just trying to do again eigen decomposition. So even this, we do eigen decomposition. We try to find the eigenvalues of this matrix M, and the eigenvectors that we get are nothing but the unit vectors that point towards the direction of the projected line that maximizes the separation between the two classes. That was a mouthful, but that was all that I was trying to speak since the past 40 minutes. Okay, so once you are able to find this eigenvalues, eigenvectors, I think it should be okay. Okay, now but again, the main thing is to understand the difference between LDA and PCA. In PCA, you are in the territory of unsupervised learning, so there is no labels. So obviously, you only have the thing that you can maximize the variance. Maybe the idea was to think about, if we have labels, can we do some more ways to reduce dimensions, making sure that the classes are guaranteed to be linearly separable. And that's why this linear discriminant analysis came into the picture. Now, there is a big proof, which was, I was thinking of actually covering that, but then I saw that it's not in the syllabus and it's very complex also. That's why I was saying yesterday that it will take time to cover LDA. But the proof is to actually prove this goal. The goal that I'm saying, that if you try to maximize JV, you are guaranteed to get classes that are linearly separable. There's a big proof on that, statistical proof. If you're interested, go ahead and read. That's fine, but it's not in the syllabus, so you can skip that. And I learned it in my master's, so that's why I thought I'll just share it. But anyways, it's not in the syllabus, so let's not go into that. And anyway, this is still a crash course. So this is about LDA. I'll give you some time, 1 minute to think if you have any questions. After that, we'll discuss this numerical example that I bought. And that way you will actually get to see how a typical question that you can solve by using LDA. This part you can ignore. This is after getting the discriminant functions and all that. This is not required. Okay, ignore this. Just how to formulate the LDA, how to get the projections, that we will learn to understand. Okay, I'll give you a minute. Okay, so yeah, okay. So no questions, right? Okay, fine. Um, okay, so we'll do numerical example as I planned. This is a slide question that we can do to understand how to solve different aspects of the LDA problem. And so what we do here is, so we are given these factors: curvature, diameter, quality, um, all these things, right? And I'll only tell you the method to solve this because I don't want to go into how to calculate mean and all. You should know that. I think that's fair, fair enough to know at this point of stage. So first, what we will do is we try to calculate the means of the two classes. C1 and C2. And C1 here may be passed, maybe not passed, right? Okay. The second step be to compute the scatter matrices S1 and S2. Okay. Scatter matrix meaning both within class and between class. And then typically the next step would be once you get the eigenvalue, you get a function, right? That is a discriminant function, and then you classify the new point based on the new based on the data point. So again, for doing the first step, the mu for past class, okay, you may try to calculate, and you will get 3.0525, and mu for not past will be 6.41. Okay, this is for the sorry. Okay, what am I doing? Okay, I'm just serious. Sorry. So you will calculate for both curvature and diameter. So uh, for the class past, right? For curvature, you just sum up the points in the curvature belonging to the class past, take the mean, you will get as 3.0525, and for diameter, you get 6.41. Okay. Similarly, for not passed, if you take the mean, you get for curvature, you get 2.67, and for diameter, you get 4.73. So this is one mean vector for past, mu past. This is a mean vector for mu not past. I call this mu past. This one is your mu not past. And these are before the projection, so you do not have the delta above. Okay. Okay. Now for now we calculate the within class scatter matrix. So I'll take the next slide. Okay. For within class scatter matrix, what we do here is for within class scatter matrix for past, right? We sum up all the data points that belong to past, okay, xi minus mu past, xi minus mu past, transpose xi minus mean past. So you take all the points xi belonging to the past category, subtract it from the mean, and take the dot product. Okay. So and similarly for the not past category, summation xi belongs to not past xi minus mu not past transpose xi minus mu not past. Okay, like this you calculate um, for the and then you calculate the between class scatter matrix. Okay, we calculate the between class scatter matrix SB and 1 second. Yeah, so yeah, so you calculate the overall mean, okay, and so, yes, sorry, you calculate this. So U1 minus U2 and U1 minus U2 transpose. Right? We already saw this formula. Right? I'm just trying to flip my notes to recall. Okay, so you calculate this thing, and then finally, uh, your discriminant function, which is the final model that you try to build, is given by W transpose X plus P, where your W you will get from the eigenvalues and eigenvectors of the matrix. SW inverse SB, that you find the eigenvalue eigenvector. You get from the, this is not important for your syllabus, but I'm just writing for completeness. Okay, you get it from the eigenvalue eigenvector of the scatter matrix. Okay. Okay, this is not. This was just to also summarize the flow of how things work here. So, wait if you have any questions. Otherwise, we'll go to the next part. Okay, okay. Let me know if you still have questions. We'll discuss. Let's go into the marathon question solving session. 20 questions. We'll give you some 2 to 3 minutes to solve every question, and then we'll discuss the answer. Right? It might take more than 1 hour, but the idea is to more get more. Sorry, idea is to get more. Uh, uh, to get more and more concepts cleared. Okay, so yeah, sorry. So let's begin. 1 second. The slide takes a while to load. Yeah, this is the first question. Okay, answer. So mean and variance of a Poisson random variable is actually the same, right? It's a fact, right? For a standard normal distribution, the mean is 0 and the variance is 1. That's why it's called a standard normal distribution, because you apply standardization procedure to get mean 0 and variance as 1. Okay. 3 fair coins are tossed independently. Let's say T is an event that 2 or more tosses result in head. S is the event that 2 or more tosses result in tails. What is the probability of the event T intersection S? Okay, answer. Yeah, the correct answer is option A. 0 is a probability. See, the event T is this. Okay, you're tossing 3 fair coins, and T is that you're getting 2 or more results in head. So the favorable outcomes are either this or this or this, or maybe you get all three as heads. Okay. S is the event that has 2 or more tosses in tails. So it is either H T T, E H T, E T H, or E T T. Okay, and as you see, there is no element common between these two sets, T and S. So the probability of this event is 0. And if you see for the matter, these are also known as mutually exclusive event because if one occurs, the other cannot occur. Okay. Yeah, I'll give more time to the next question. Yeah. Okay. Okay. So yeah. Okay.
You are currently the only person in this conference.
Okay. So yeah. So it's like this. See, let's say there is a linked list like this. So 1, 2, 3, 4, and null. You are given a pointer to this node here, 3, and you want to delete 3. Okay. How do you delete it? See, I have access to the next node. First I will do is I will copy the value 4 over here. And then I will delete this node. And how many steps you need? Okay. Okay. Check this out. Okay, so you're given a pre-order traversal. So it's 15, 10, 12, 11, 20, 18, 16, 19. Now it's a BST. Okay, it's a BST, binary search tree. So what you do is if you sort this array, right, you get the in order. Because in order of a BST is a sorted tree, right? So so what you do is this is a pre-order. So first your root of the tree contains 15, right? So you mark 15 here in the in order. Your left subtree contains these elements. Obviously they are less than 15. But which is the root? The next element is 10 here. So 10 is the root. You mark 10 in the in order. Okay. Now these are right subtree, right? 11 and 12. Which one comes first? Look at the pre-order. 12 is processed first. So this will be 12. Mark 12. And the left of 12 is 11. So you mark 11 here. Okay. So this is done. Now in the right subtree contains these elements. Which is the root? Look at the first element in the pre-order. You process the root first, right? So it is 20. So 20 is the root. You mark 20. Now each of them are the left subtree of 20. Which is the root? 18 is the root. Okay. Mark 18 in the in order. Left is 16, right is 19. Left is 16, right is 19. Now if you try to find the post order, you will go left, then right, then root. So left, you reach 10, it's a subtree. Left, there's nothing. Right, there's a subtree 12. Left, so first you process 11. Right, there is nothing. Then you process the root. So 11, 12. Then you process the root 10. Now this left subtree is processed of 15. Now you go to the right subtree. This is a subtree again. Left subtree, it's a subtree again. So 16, 19, 18, 20, 15. Is there an option? 10, 16, 19, 18, 20, 15. Option C is the right answer. Okay. Why do we get overfitting? Because of dash bias and dash variance. Okay, so we get an overfitted model if we have low bias and high variance. Okay, this is very important concept. You must know bias variance trade-off. Please watch that video. Okay. The worst case runtime of insertion sort, merge sort, and quick sort are worst case. Option D. N square is the worst case for insertion. What is the best case of insertion sort? What is the best case? N. What is the best case of merge sort? N log n. What is the best case of quick sort? N log n. Okay. Okay. Try this out. Okay. So it's a hash table with 9 slots. So let's say this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 slots. And the hash function is k mod 9. You resolve collisions by doing chaining. You insert the key 5, so 5 goes here. You insert the key 28, it will go here because 28 mod 9 is 1. Again, 19 goes here as well. 15 will go here because 15 mod 9 is 6. 20 mod 9 is 2, so 20 will go here. 33 mod 9 is 6, so 33 goes here. 12 mod 9 is 3, so 12 goes here. And 17 mod 9 is 8, so 8 goes here. 17 goes here. 10 mod 9 is 1, so 10 goes here. So the maximum chain length is actually 3. Sorry, 3. Minimum is 0. Oh, sorry, the average is either 1 or 2. So what is the average? So 3 plus 1 or 0 also. So 0 plus 3 plus 1 plus 1 plus 0 plus 1 plus 2 plus 0 plus 1 by 9, which is 5, 6, 8, 9, 1. So is the right answer. Okay, average length is 1. Okay. Same another question on hashing. Okay, yeah, this is hash to the same value. Sorry, not hash. Okay, so given the following input, x mod 10 is the hash function. Very easy hash function. Just look at the last digit. That will be the hash x mod 10. So 9679, 1989, and 14199, they hash to the same value. It's a true statement, right? All of the last digit is 9, so it's true. 1471, 6171 also hash to the same value, so it's the same. All elements hash to the same value. No, that is not true, because if you take 4322, 1334, this hashes to 2, this hashes to 4. So they do not hash to the same value. Each element hashes to a different value. No, if that was true, then 1 and 2 would not be true. So again, 1 and 2 are the right statements. Option C is the right answer. Okay. Oh, same question. Okay, then you have less question. 20, no, 19. Let M be a real 4 by 4 matrix. Okay, not 44. Consider the following statements. M has 4 linearly independent eigenvectors. M has 4 distinct eigenvalues. M is invertible. Which of the following is? Okay, so yeah, so M can have four linearly independent eigenvectors, but it should have four distinct eigenvalues. Then only it can have four linearly independent eigenvectors. So option B is the right answer. S2 implies S1. Okay, this one is easy. Try to find the limit of this function. Yeah, without solving, I can solve this in my head now. Okay, fine. Yeah, yeah. So first you check limit x tends to 2 root x minus root 2 by x minus 2. If you plug in the value of 2, you get a 0 by 0 form, which is an indeterminate form. You can apply L'Hospital rule. People call it L'Hospital rule. Okay, that doesn't matter. You differentiate the numerator and denominator separately. So if you differentiate root x minus root 2, you get 1 by 2 root x. And if you differentiate the denominator, you get 1. So, okay. So limit x tends to 2, 1 by 2 root x is 1 by 2 root 2. So 1 by 2 root 2 is the right answer. Okay. Hey, okay. Repeat. Yeah, this is a very good question and very controversial question as well nowadays. Many people try to answer it differently. Okay. Okay. So to explain this answer, I'll try to explain it with an example. Okay, real life example. Let's say you are a model being trained to prepare for the GATE exam, and I throw at you a lot of GATE PYQs. Let's say till the history of GATE exam, I throw you all the GATE PYQs, the question, the answer, and the solution. Now there could be two ways people prepare. One is you mug up the PYQ answers. Okay. All the PYQ previous year questions that are there, you just mug up the answer. Okay. Just learn it by heart. What will be your training error in this case? Which means if you try to again solve the PYQs after mugging up, your training error will be zero. I'm assuming you are able to mug up perfectly, okay? So it will be zero. It's a good model, right? Will you pass the gate with this? Answer is no. Because obviously you didn't understand things, you just mugged up the answer and you went to the exam. What we can do is, second technique is that you may understand the solution, learn the underlying concept. Okay, let's say you took a problem, you saw that there is a concept involved, so you learned the concept, and then you try to do it. Is this a better way to doing things? Yes. So your training error in this case will not be actually very zero. You might still have to, because you're just understanding the solution also, it will be but approximately close to zero. And this way you will pass the GATE exam. So one way to understand this is if you have mucked up the PYQ answers, you are not going to pass the GATE exam, right? So the other case, if your training error is zero, if you are perfectly your predictions, whatever you try to answer the questions, if they are same as what they were originally, your training error is zero, but you will not pass the exam. But instead, if you generalize things to a greater aspect, if you look at the concept and if you understand, then the training error will be close to zero. Let's say someone actually mucked up all the PYQ answers. Okay, mucked up all the PYQ answers, and the problem now is uh, that his training error is zero. So he has overfitted the model, he or she. What can he or she do to mitigate this situation? Okay. So what I will do to help him train better. So if you are falling in the first category, what I will do to do is I will introduce randomness. I'll just add a few twist question. Okay, some questions which have a few twist from what is given. So I'll introduce some regularization. Okay, I'll try to penalize the student by introducing some twist questions, some random questions, and that way the student will realize that boss, even if I mug this, he will tell another, and like this, that's not the right way. So he will be bound to transition, he or she will be bound to transition to the second category. But reducing model complexity always works to reduce overfitting. Okay. Other way is I gave him, let's say, 100 questions and he mugged up 100 questions. I will give him now 1 lakh questions and tell him now try to mug it. Obviously, the students won't be able to. So I will increase the training data. These two are classical methods of decreasing the overfitting. And the fourth option is increase the number of optimization steps. It's more like I'm telling you, boss, if you have learned till, let's say, you have revised it 5 times, why don't you revise one more? And that way your model will be better. The thing is, you will again revise the same thing, right? So this is not correct. 2 and 3 is the answer. Few people argue that 1 is also the answer. See, the 1 is very funny if you answer it. Okay. In one way, you can say that, let's say my training error is what I'm trying to do is I'm trying to see if that person, whatever he is trying to, loss function is like what I'm trying to say is I'll change the loss function. That's not the right way because it's more like if the student may say that, boss, you are evaluating my model, I will change you. I will get some other person, right? But the training method is still the same, even if you change the loss function. So you can still overfit the model. So I don't know why people are answering this as correct. This is not correct. This is not basically not logically correct because it might seem that it's more like, how can I explain? Like I explained, right? For example, I was evaluating your model, whether you are studying for the gate or not, and then tomorrow you might change me. Does that make your model better? Does that reduce the overfitting? It may not, right? So this is not correct. So that's why B is the right answer. Take it that simple. I just explain it with a real life example. Changing the loss function may or may not reduce overfitting. It's not that it is always reduce overfitting. But if you reduce the model complexity, if you increase the training data, it will reduce overfitting. Okay, because it will increase the bias, lower the variance of the model. Okay, it's a very, very good question. Try this out. Very good question. Okay, so it's a very interesting question. So, okay, see, let's look it in set theory terminology because it's all given in set, right? So we have the universal set. Okay, let's draw the universal set. We have the universal set U. We have a set A, which can be said as the event A. Okay, and B is a subset of A. So this is B. Hmm? So the probability of B is nothing but the probability number of elements in B, sorry, divided by the number of elements in the unit set, the universal set. Everyone knows this. Similarly, probability A is the same. The probability of B conditioned on A is nothing but probability of A intersection B divided by probability of A. Probability of A intersection B, what is it? It's nothing but the probability of B. Okay. So the first inequality says the probability of B given A is greater than or equal to probability of A. Okay. This is true. What do you think? Okay. So probability of B intersection A is less than or equal to probability of B. Is this true? No. So A is true. A is true. Probability of A given B is less than 1. That is always the case because probability should be less than 1. Probability of A given B cannot be 0. Okay. Increasing the regularization coefficient value for a ridge regression will do what? Okay, so if you increase the regulation coefficient, your overfitting will reduce, right? Which means you will decrease your model bias and you will sorry, increase the model bias and decrease the model variance. Option B. Oh, same question again. Yeah, for a matrix H, one of the eigenvalues is 5, then the other eigenvalue is Okay, so remember these two things. Okay, so the trace of a matrix M is sum of eigenvalues. Trace of matrix is sum of eigenvalues, and the determinant of matrix M is the product of eigenvalues. Please remember these two things. Okay. So the trace of the matrix is nothing but the sum of the diagonal. Sum of the diagonal is 15. One of the eigenvalue given is 5. Other will be 10. Simple, right? You might do the calculation and all, that is not required. Two eigenvalues of a 3 by 3 matrix X are this and this. The determinant of the matrix is what? Again, right? Just explain. So determinant of matrix X will be the product of the eigenvalue. And one thing you must know is, if a eigenvalue is complex, then it always occurs in conjugate pairs. So when you take the multiplication, you say 1 plus I, and you write the conjugate and then multiplied by 2. This is nothing but 1 minus I square multiplied by 2. 1 minus I square, 1 minus of minus 1, 1 plus 1 is 2, which is 4. Determinant of the matrix is 4. Okay, the function f of x has a dash. Okay, so if you differentiate this function with respect to x, you get 1 plus 2x. You equate it to 0, and then you get the value of x as minus 0.5. Okay. Now, if you do the double derivative, you get 2. So at 0.5, it's still 2. So positive number, so it is a minima at x equal to minus 0.5. Maxima would occur if it's a less than 0 value. Saddle point would occur if it is 0. Okay, now this is Pearson correlation coefficient you have to calculate for a data given below. Now, what is the formula for Pearson correlation coefficient? So Pearson correlation coefficient given by R is nothing but the covariance between x and y divided by standard deviation of x, standard deviation of y. Okay, now you have to do the math. So first, if I try to calculate the covariance of x comma y, okay, which is summation I equal to 1 to n xi minus x bar yi minus y bar, and you take the average 1 by n. Now x bar, if you calculate, you will get as 0.16 negative, and y bar, if you calculate, you will get as 4.9. And so the covariance that you get is minus 23.08 divided by 5. Similarly, you will calculate the standard deviation of x given by root over 1 by n I equal to 1 to n xi minus x bar whole squared. And similarly, you will calculate sigma y root over 1 by n I equal to 1 to n yi minus y bar whole square. And then if you plug in the value, you will get the value of r as minus 0.474. The correct answer is minus 0.5. Okay, with this, I have covered a good amount of questions that I had. I think we have just on time, so I'll end the lecture here. Thank you. All the best for your exam. Do well. I'll wait if you guys have any questions before ending the lecture. Sorry, for every time I asked today, I forgot to ask. Meanwhile, no questions. Okay. Thank you very much for joining.